Welcome to Chemistry at Hononegah High School. I'm Brian Brown, and today we'll be doing a review of ionic and net ionic equations. And where I want to start is looking at a particle level, what's happening. So if we have aqueous silver nitrate, we don't really have AgNO3 as a unit in the solution. If it's dissolved, what's happened is it's broken apart into its component ions. So while it is Ag and NO3 split apart, the problem with those is those appear to be neutral, and what we really have are ions of those two things. So what we really have is every AgNO3 that breaks apart, we get one Ag plus and one NO3 minus, and that's what's actually in solution and floating around. And those things are uniformly mixed up to make our solution. So really this looks heterogeneous at this point, but in the real world, it would be a homogeneous even mix. Same thing happens with KCl. That's another aqueous ionic compound. So what we really have is K plus and Cl minus in solution. And that's what's happening at a particle level. So when we write it as AgNO3 aqueous and KCl aqueous, that's really an oversimplification of what we actually have in the solution. This is a much better look if it were uniformly mixed together of what's actually happening at a particle level. Now, if we take these two beakers and we mix them together, so we dump them together, what's fundamentally going to happen is all of those ions are now going to be in the same beaker floating around. Now, what you have to do is understand that when those ions mix up, oppositely charged ions will attract each other, so it's possible they may precipitate out and form a compound. But if they're water soluble, as soon as they would attract, they would redissolve and they'll stay in solution. But if they form an insoluble product, then what you end up with is a precipitate forming. So right now, while this is true, that's what we'd have floating around. What actually happens in the situation is AgCl is insoluble. So as soon as an Ag, and that's what you see right here, gets together with a Cl minus, when they come in contact, they actually combine to form solid silver chloride. And that happens throughout solution. And while we're still going to have K plus and NO3 floating around because potassium nitrate is water soluble, so they're going to stay in solution, the silver chloride solid is going to precipitate out. So if we dump in enough ions to reach to go beyond the solubility of silver chloride, we see a precipitate forming. And that's really a more accurate look at what's happening inside the beaker in a double replacement reaction. Now, if both of these are water soluble, then the ions are just mixed together floating around. That's a physical reaction, not a chemical reaction. And you have a precipitation reaction that doesn't end up occurring. It's a no reaction as an ionic and a net ionic equation. Now, if we're going to write net ionic equations, it's really a three-step process. Wait till the bell is done ringing. First, we have to get what's called the molecular equation, and doesn't mean we're talking about molecules, we're talking about things together as a unit in their molecular form. And then from there, we're going to end up making the complete ionic and then the net ionic equation. And here are the steps for doing those three things. First, in your double replacement reaction from first year chem, you basically swap the cations. You looked at the new ions or ionic compounds that were formed based on charges. So you would do your double replacement and predict your products. And remember, don't forget to check charges and make a neutral substance to get the right formulas for your products. Then you'd balance the equation to fulfill law of conservation of mass. And then from there, we need to look up what the states are. So we need to check our solubility rules and see if our two new compounds are water soluble or insoluble. Because if they're insoluble, then they're going to precipitate out as a solid, and our state would be S for solid. If they're water soluble, then they're just going to stay as ions, and writing it as KNO3 aqueous is just a simplification and a convenient way to write it. It's not necessarily accurate. And then also remember, if you make HOH, that's just water, so we call that a liquid. And then finally, it's possible that we could end up getting a gas like carbon dioxide or hydrogen sulfide. There are gases that could end up forming in that double replacement. Next thing, once we've got a balanced molecular equation, now we're going to make it a more realistic look at what's happening at the particle level by turning it into an ionic equation. And then all that really means is we're going to split any strong aqueous substances into their component ions with proper charges, proper formulas, proper coefficients, and proper states. And then from there, we're going to cancel the spectator ions to get the net ionic equation. And in the end, we should also be able to identify if we've got a precipitation reaction or an acid-base neutralization. Now, a couple of things to remember about step 1 in part 3, because you've practiced the 1 and 2 before. But determining states is something that you did in honors chemistry, but maybe not in other levels of chemistry. First, if you end up with an ionic compound, remember metal, non-metal, cations, anions would be ionic, and it turns out to be soluble, that's going to be an aqueous state. So think of it like a fourth state of matter. It's one that would be unique to solids that are water soluble in water. If it ends up to be insoluble, then it's going to stay in its solid form. Remember, if we get HOH, that's actually liquid water, and if we get H2CO3, that's aqueous. This is something I've seen before in the AP test. It's been a while, but because of that, and because it's such a common reaction, it's something that I do want you to be familiar with. If your double replacement gives you H2CO3, carbonic acid, that is unstable in the situations that we're going to be looking at. So aqueous H2CO3, you need to know that breaks apart into H2O liquid and CO2 gas. And that's one you just have to be familiar with. In the lab, when we neutralize acids with baking soda, it's this kind of reaction. The reason why it bubbles and fizzes and neutralizes is it's an acid reacting with a base, and it's going to end up forming H2O and CO2 in the neutralization process. Finding the states and doing all that together, let's run through it one time. If we have silver nitrate that's aqueous and calcium chloride that's aqueous, remember what we're doing is we're flipping the cations and the anions. So in the process of these two things being added to one beaker, the silver ions are going to come out of solution, and the nitrate ions, let's just put them down here as separate, those things are going to come out in solution in this form. For every one AgNO3, we get an Ag plus and an NO3 minus. And for every CaCl2, we get one Ca2 plus, and we get two Cl minuses. So when we do our double replacements, that's what we're really having to work with. We're going to take the silvers and the calciums, and we're going to end up trading places. Now, when you put them together, it's really critical that you are appropriate with charge, because you can see our problem right here. If we just literally switch them up and wrote down what we would get, we don't end up forming a neutral ionic compound. So we have to find out using and based on the charges in step 1 what the correct formulas are. Now Ag is a +1, Cl is a -1, so it's just going to be one of each. We're going to form AgCl. And then the calcium is a 2+, with the nitrate that is a -1, we need 2 of those. So that will end up being what we get in this process. Now, we're done with step 1. Step 2 would be balance. Well, right now, it looks like my problem would be I need 2 chlorides on each side. That gives me 2 silvers, and that would then give me 2 nitrates, but I've already got 2 nitrates in the calcium nitrate. That's my balanced equation. And then finally, we would check the activity series. Nitrates are always soluble, so I know when I look that one up, this one's going to be AQ. And silver chloride, we just looked at a second ago, that's an insoluble substance, so that's going to form a solid. And that would be writing the molecular equation. And keep in mind, the right side here and the left side has formulas that are written technically inappropriately. CaCl2 aqueous isn't really CaCl2. It's broken apart into its component ions. And that's where the next process comes in. Writing the ionic equation. We basically appropriately split things as they really exist. So when we take our balanced equation from a second ago and we split it into its component ions, remember this is 2 AgNO3s. So what we're going to get is 2 Ag, and that's the positive ion, and 2 nitrates, and that's the negative anion. So that's what we really have when those two things split apart. And yes, it's aqueous, so that's what we would put for both of these. And that's really what we get from our silver nitrate. Now we also, on the reactant side, have calcium chloride that's aqueous. That's going to split into its component ions. And we're going to get twice as many chlorides as we get calcium ions. And remember, Ca is a 2+ charge, and Cl-, and let me actually swap out that 2 for a more appropriately sized 2. And remember, those are going to be floating around in solution. So that's really everything that I have on the left side as it really exists inside the beaker. And then we do the same thing on the product side. Now, the first case, we have AgCl solid. That's not aqueous. That means it's going to stay together as a unit. So we're just going to have that exact same thing here. And with that, we have calcium nitrate, which is aqueous. So just like on the other side, that's going to break apart into its components. Let me get the correct ion charges in there. And then we're also going to have nitrate. And remember, this 2 means we have 2 nitrates forming, and that's a -1 ion. And once again, these are aqueous, so I'm running out of room here. And that would be our what's called the ionic equation. We split any strong aqueous substance, so strong acids and soluble ionic compounds like silver nitrate, calcium chloride, and calcium nitrate. Now, a couple of other quick things, because we're going to come back to this in a second. I've got a couple of other that I want to hit real quick. Remember, here we had all 3 soluble ionic compounds and 1 insoluble ionic compound, but we can also have acids and bases, and those can be either strong or weak. Remember, we want to write it in its ionic equation in its predominant form. And if it is a weak acid, like the one that I've shown here, acetic acid is a weak acid. So when we throw it in water in its aqueous form, yes, it does break apart to a small extent to make H plus and the acetate ion, or anion, C2H3O2-. It only partially ionizes. So most of it stays together as a unit, and we get some ions from it. So it would be more appropriate if we look at this weak acid to leave it together in this form. So while it is true that you would think, and it looks like I don't have it animated to split, that you would break this into H plus and the acetate anion, as a weak acid, it stays together. But something like HNO3, which is also an acid, that's one of our strong acids, we would split this apart into its component ions, just like we did with the ionic compounds that were water soluble. So remember, strong split, weaks don't. They stay in their molecular form. And if you put it all together and make it pretty, that's what the last one looks like. So that brings us to the third step in the process. Anything that is just floating around in the water before and after is what we call a spectator ion. It's there watching the reaction occur, but not actually involved in it. So to get an ionic equation, all we do is cancel anything that does nothing in the reaction. So you basically go through and take a look at what seems to do nothing. I have 2 silver ions on the left, but over here on the right, my silver chloride, those ions aren't floating around, but my nitrates, I've got 2 here and I've got 2 there, those did nothing. My calciums, I have a calcium ion here and a calcium ion there, that did nothing. So if I reduce it to what actually reacted, it looks like I have 2Ag plus aqueous, making 2Cl reacting with 2Cl minus ions to form 2AgCl solid. Now at this point, because I've got all 2 coefficients, we could reduce that into Ag plus Cl minus makes AgCl. So that would be an example of a net ionic equation. Cancel your spectators, that's really all you do for the net ionic equation. And remember, it does still have to be balanced in the end. Now, one thing to watch out for is if nothing was insoluble, you would end up with a bunch of ions on the left, a bunch of ions on the right, and they'd all cancel, and you'd be left with a no reaction situation. So remember, if everything is aqueous and they're all strongs, they're going to split into their ions completely on both sides, and therefore nothing really happened chemically. It was just a physical mixing of the 2. Now, quick reminder of our 2 different types of double replacement reactions that we've got to be able to identify for this chapter. We've got precipitation is one of our products, an insoluble solid, and then we have acid-base neutralization. And honestly, the easiest way to look at this is if you ever get H2O, remember also HOH is H2O, or if we get H2S, which is actually a gas, not a liquid, you would end up with a acid-base neutralization. And with the ones that we're going to be looking at, it's easier to handle it from that point of view. If you ever get water H2S, acid-base neutralization. If not, it's going to be precipitation. And remember, even if it's a no reaction precipitation, we would still term it a precipitation reaction. Now, in a normal acid base, we have a metal hydroxide, reacting with a acid. And sometimes, because we're early in the year here, you might not know what substances are acids and bases 100%, because there are some things that don't look like acids and bases and really are. But if it's a metal hydroxide and something that starts with an H, it's going to end up in acid-base neutralization. Remember, if you get water, you know is acid-base neutralization. That's one form. The other one that your book mentions that I want to make sure you at least have a working understanding of is sulfide would be an example of one of those things that's a hidden base. It's actually accepting a proton, which is what bases do. It's just that until you know more chemistry, you might not know that's what would happen. So if you form water or H2S, then you have an acid-base neutralization. The other one to watch out for is one we already talked about earlier, which is carbonic acid, H2CO3, if that's what you get from double replacement. Don't forget to decompose it into CO2 and H2O rather than leaving it in its molecular form. It's actually going to become those two compounds. And that's, I believe, it.